complicated, but only in terms of writing. It's not more complicated conceptually. If you concentrate on the phase x, you have a flow. So let's concentrate. I hope that everybody can see here. Let's focus on the direction x. And here you have one face of the direction x of our cube, and you have here qx, lowercase qx entering. The other face along x of the cube is located here after a distance dx. Let's suppose that you have a flow through here. A flow that exits from the cube. What is the amount of this flow? It will be qx, lowercase q, plus the derivative of lowercase qx with respect to x, it's a partial derivative, times dx. If I have qx here, on the other face, the opposite one, I will have qx plus derivative of qs, partial derivative, with respect to x, times the x. Again, it may go to 0. The flow in the opposite phase, it's allowed to be 0. There is no limitation on the amount of flow. And therefore, if I take the sum along the three components, then I get, as a result, q out. Q out is equal to qx plus partial derivative of qx with respect to x times the x, the y and the z again, plus the other two components. So it's nothing difficult. And so far we only assume that the flow is incompressible and that we have no source terms inside the control volume. Okay, very good. Now, again, don't be concerned, it's nothing difficult. Now we can substitute into the mass balance equation that we wrote before. And therefore, as a result, this is just a substitution. There is no other step here added. If you look, this is basically the mass balance equation. Change of volume in time is given by q in minus q out. Q in is given by the sum of the three terms that you see on the first line. Q out is more complicated because, as you remember from the previous slide, it's a bit more complicated. It's given by the sum of the three components that you see in the second or third line here, in the minus, because I am subtracting. Okay, and you may notice that there are terms that compensate each other, they eliminate each other. So if you look at the terms lowercase qx times the y to z, it's the same term that is subtracted here, times the y to z. They eliminate each other. So the three terms on the left-hand side, first row, lowercase qx, lowercase qy, and lowercase qz, they are the three of them eliminated one by one by the first addendum inside these parentheses. So the result is that what's surviving is only the second term, partial derivative of qx with respect to x times the x. This is the only surviving term into each of the parentheses. And in fact, you can see here, the last line, this one, it's the sum with the minus sign of the three surviving terms. Partial derivative of qx with respect to x times the x times the y to z. So you see that the mass balance equation remains in a quite simple form. So partial derivative of w with respect to time is equal to partial derivative of the flow components in each phase with respect to the same direction times the x, the y, the z. Okay. Now we have to introduce a definition, which is the volumetric specific storage. What is the volumetric specific storage? We call them with the symbol SS. I wonder whether, let me see. I would like to get some more room in the blackboard, but I am not sure how I can move. Okay, let me try. Let me try. Okay. Okay. Now I removed and I kept the definition, which is what I want to concentrate on. So let me now getting the blackboard clean. And let me define this quantity volumetric specific storage SS, which is it's an extremely important property of the aquifer. It's an hydraulic property. It's not what we may call a physical property, but it's strictly related to the physical properties of the aquifer. It is strictly related to the aquifer porosity and also permeability. So, SS, what is SS? Let's read the definition. It's it can also be called specific storage. SS comes from specific storage, actually. It's the volume of water that an aquifer releases from storage per volume of aquifer, so per unit volume of aquifer, and per unit decline in hydraulic head. Okay, so again, volume of water, which is released by an aquifer, per unit volume of the aquifer. So you understand that volume per volume is adimensional, and it's strictly related to the porosity of the aquifer, because if the aquifer has zero porosity, of course it cannot release any water, because it's volume of water per volume of aquifer. Okay, and you may think this may be at most equal to 1. No, it may be more. I'll explain. So as you get water, water may come in. So it's volume of water that is released, again, per volume of aquifer. You understand that in order to release it, the aquifer has to have pore connected, because if they are not connected, if there is no permeability, water is into the aquifer but cannot be released, unless you get, okay, you get the single pore, you get the water that is into that pore, but then it's done. So basically it tends to zero if there is no permeability. But what is the driver? I mean, what is the driver originating this water flow? Because if the aquifer has to release water, there must be a flow in it. So what is the driver? We need energy. We need energy to allow this flow to occur. So the driver is the unit, decline in hydraulic head. This is the driver. This is the energy input. And now we have to recall what is hydraulic head or hydraulic energy. I'm not sure whether I already discussed with you the Bernoulli theorem. I already discussed it with you? No, probably not. So let me now recall in 3 minutes what is hydraulic head. It's also called hydraulic energy. Is an estimate of the energy of the flow. So if you have water flow, you understand that you have water moving, and it means energy. Because water is weighing, so the weight of water is a force, and force times a movement means energy. So how can we measure the energy of the water flow? We go back to Bernoulli theorem, which says that the energy of a water flow is given by the sum of 3 components. There is a potential component, there is a kinetic component, and there is a pressure component. Kinetic, you know, you remember, derives from movement. So a body that is moving is a body that has energy due to the velocity. Potential energy is something that is related to the placement of the body. If the body is at higher elevation, has more energy than a body at lower elevation. We remember that. There is the pressure component. The pressure component means that a body that is under pressure has more energy than the same body at the same location at a lower pressure. If you think about like a ball of football, if you compress it, when you release the pressure, then you have a sudden expansion, which means that the expansion takes place at the expense of energy. So pressure means energy. These recalls of fluid mechanics are not included in my slides. My slides just say hydraulic head. And I'm saying this in order to inform you. You are not at the exam required to explain to me what hydraulic head means, but you have to understand what it means, because I realize if you don't understand, I wouldn't ask you, I will not ask you what is hydraulic head, but I will understand if you don't have any idea what it means. So basically I'm explaining to you that hydraulic head means energy of the water flow, and also it is given that it's potential energy for a component, it's energy of water. And I think I made an imprecision when I defined it. It's energy of water. Water intended as a body. Okay? So what it's important that you understand that hydraulic head means the energy of a water body or a water particle. And you have to understand where it comes from. So basically, Bernoulli theorem says that the energy of a fluid particle, this is what Bernoulli theorem says, the energy of a fluid particle is expressed by three components. A potential component, which is the location of the particle with respect to a reference. So, and in particular, it's the height of the particle with respect to a reference level, Z, okay, with respect to zero level that you may fix wherever you want, plus a pressure component where P is pressure acting on the fluid particle divided by the specific weight of the fluid, gamma, water in this case, plus the velocity squared of the fluid particle divided by 2g, where g is gravity. And there is here a coefficient alpha, if you remember something of fluid mechanics, which is close to 1, and therefore we neglect it. Perfect, this is the hydraulic head. What is the hydraulic head? The measure is a length, the unit is a length, and so how can it represent an energy? It's the energy for unit weight of the fluid. And this refers, the basic formulation of the Bernoulli theorem refers to a fluid particle. It can be extended by integration to a control volume. We don't do that. We just want to say that whenever you define a control volume of water, you can define an hydraulic head for this control volume, which is the average of the sum, which is the same of the head of all the fluid particles in it, and the hydraulic head is given by three components: position of the control volume, pressure along the control volume, velocity of the fluid in the control volume. Of course, if it is a control volume, it's average velocity of the fluid particles. Keep in mind an important assumption that somewhere it's introduced in groundwater models. Given that the flow is very, very slow, we neglect this. Typically we neglect this. And then, if we neglect it, how can we measure the hydraulic head for an aquifer? And let me depict an aquifer here. First, an unconfined one. So let's suppose that this is the surface. You have houses here, you have people. The scale, of course, is not correct. And you have in the underground a water table. Usually I indicate with this kind of sign, kind of S, water surface. And with the ground is indicated with just a line with people over it. And this is called water table. What is the water table? Is the divide between the saturated zone, so this is saturated, this is unsaturated. Even if it's unsaturated, there is water into it, of course, but it's below saturation. The water table is the divide between saturation and unsaturated. There is water here because for capillary forces, you may have water going up from the saturated zone to the unsaturated, and also you may have infiltration from the ground. So if you have infiltration, basically it's water that goes into the ground for after rainfall. You get water infiltrating into the ground and eventually reaching the water table, the groundwater body. But this is the water table, which is your divide between the saturated and the unsaturated zone. Typically, the water table, if you go, when you were a child, probably you tried on the beach to dig an hole in the sand, and after a while you eventually found the water of the sea, the salt water coming from the sand, reaching a certain level into the hole. This is the level of the water table. So the level of the water table is the same level that you see into a well. If you're well entering into the water table, of course, the well is like this. And if you look into the well, you measure, you see into the well the level of the water table. Keep in mind that in order to make this measurement, in order the well to clearly indicate the level of the water table, you need not to pump from the well, because if you pump from the well, the level into the well goes below the level of the water table. But in static conditions, the level of the well gives to you the level of the water table. And the water table, being the separation between saturated and unsaturated zone, has a relative pressure of 0. You have atmospheric pressure over the water table. So over the water table, you have pressure here, which is 0, and therefore the hydraulic head is given only by the level of the water table. So if you get a fluid particle here, this fluid particle has a pressure of 0, and therefore its energy is given by only the level of the water table. And for the hydrostatic law, the hydraulic head that the particle over the water table is the same for all the particles in the aquifer. It's the hydrostatic law. Let me not record the hydrostatic law. There is the law on Wikipedia, and if you don't remember these concepts, you have the means. Please get them back, record them, you have the means. If you find any problem, just ask me. I don't want to go into more details because I have the concept that I may become too trivial. I'm sure that some of you already remember what is the hydrostatic law, what is the hydraulic head, so it's a measure of energy, so I don't want to go to spend too much time with it. But if you have concerns, just let me know. Okay, so the important conclusion is that for an aquifer like this, which is unconfined, the hydraulic head is given by the level of the water table. And therefore, what does this mean? It means that if you get water from the aquifer, you have a decline in the hydraulic head because you have a decline of the water table. And for unit decline of the water table, you may get less or more water. The measure of the volume of water per unit volume of aquifer, unit decline of the water table that you get from there, it's the specific storage. If you have a lot of permeability, the water table declines just of a small amount if you get water. Because it's replenished, it means that the aquifer has a high specific storage. Okay. Just on this case, one more specification. The water table, you may wonder whether it's horizontal or not. And you may think it's horizontal because it's a water level. Keep in mind that it's horizontal if water doesn't flow. If you have a water flow, it's not horizontal. Like for a river. A lake, why a lake has a water level that is horizontal? Because water is not flowing. If you look into a river, the water level is not horizontal, it's tilted downstream because water is flowing. In the aquifer, water usually is flowing very slowly, which means that the water table we expect that is almost horizontal, but if there is movement, it's not. Okay. Second case, confined aquifer. Let me make another drawing here, very simply. So again, people here, and then you have a confining layer. And you have here the aquifer. It's under pressure, so it's a different situation, it's artesian. But if you dig a well into here and you get through the confining layer, what happens here? It happens that water flows over the ground. Very good, because I don't have to spend energy to get it. But if I assume that I can heighten the well, there will be a limiting height reached by water. Because you understand that water comes from mountains, comes from high, so it goes above the ground, but there is a limiting height, which is given by the energy of water, of course. And then it may be here. And this is the measure of the hydraulic head. So even for a confined aquifer, you can get a measure of the hydraulic head of the aquifer, which you may take if you dig what is called a piezometer. It's a kind of tube that doesn't limit its height on the ground, but can be heightened. Okay, so we understood what's the water head, the hydraulic head of an aquifer. It's the level that the aquifer reaches at the atmospheric pressure in that point. So, again, it's the level that water into the aquifer reaches at the atmospheric pressure. So we have an aquifer, we take water, and the water table declines, the amount of water released by the aquifer per unit volume of the aquifer itself, and unit hydraulic head decline is specific storage. Therefore, what can we say thanks to specific storage? We can say that, one second, let me see if it's only one picture. One by one, otherwise it becomes too messy. We can say that we can write the mass balance equation in this way. So, the change of volume in time, it's given by specific storage, times change in head, times volume of the aquifer. Clearly, change of volume in time into the aquifer volume of water is given by specific storage times change in hydraulic head in time. This gives the time change times the volume of the aquifer. Okay, so of course this is another way of writing the mass balance equation. Now we can equate the right-hand side to the right-hand side that we previously derived. So, So, basically, the right-hand side is equated to the right-hand side that we previously derived. And therefore we obtain this. This term here is the same as the right-hand side that you find up there. So the right-hand side is the same. The left-hand side is substituted by that we previously derived. Nothing difficult. The only problem here is to remember these steps, but it's really very easy so far. And then let me see the final step, which is just so basically, if we rearrange what we previously found, we get this simple relationship in the upper line, and we realize that the left-hand side is just the divergence of the vector q. If we identify a vector that describes the water flow per unit area, and we indicate it with q, whose components along the three directions are qx, qy, and qz, we can write that the divergence of it's divergence or it's I have a numbers now, I can't remember. Anyway, this is the operator. I think this is the nabla operator that takes the three derivatives along the three directions. It's called nabla, I think. Anyway, you understand? It's an operator that takes the three derivatives along the three directions of q, okay, and sums them. So minus nabla q is given by SS times the change in time of the hydraulic head. It's not yet divergence, it will become divergence later. Okay, this is another way of writing the mass balance equation, but we have introduced a very important hydraulic property of the aquifer that is unknown. It's unknown. Okay. Let's move forward. And now we have to take into account that the equations that we just derived, so nabla q minus nabla q is equal to SS times derivative of h over t. This equation has both the flux and the head unknown, and therefore we need a second equation, which we perfectly understand, because so far we spoke about mass balance. We know that energy balance is an essential component, and therefore it is necessary to couple the mass balance equation or continuity equation with the second equation, which is the momentum equation. Okay, and at this stage we need to introduce this momentum equation. What is the momentum equation? It is an equation relating the flow to the energy of the flow. So it is an equation relating Q with H. It is an equation relating the flow with the hydraulic head. So, what kind of equation can it be? We know from the linear reservoir that we adopted an energy equation that was very simple. You remember, it was a relationship between the storage in a catchment and the river flow. It's the same thing. Here we are looking for a relationship between the flow and the head, flow and energy. Storage is a synonym of energy, because storage, if you remember, it's a level. In our linear reservoir, it's a level, so it's similar to an energy. So we are looking for a relationship that relates, again, flow with energy. You may have studied in your past the open channel equations. the open channel equations, and in particular the Saint-Venant equation. I'm not assuming that you know them, but if you remember them, the Saint-Venant equations, which are the open channel flow equations, the momentum equation relates the flow through variables, hydraulic variables, height of the river flow, water level, velocity of the current, which means relates flow to what? To the, I don't remember the name through the energy spent by the flow. In English I don't remember. In Italian is the cadente piezometrica, but cadente dell'energia. In English is called, I don't remember, friction losses. Friction losses. Relates basically the flow to friction losses, which means, again, a relation between flow and energy. Now, for an aquifer, what kind of relationship can we devise? Okay. So there were a famous hydraulic, I think he was an hydraulic engineer, I think he was French. Darcy made an experiment, and there are links on my web pages. He made an experiment, a series of experiments to identify a relationship between, in an aquifer, the flow and the energy. And therefore, what he did basically was to push water through a sand tube. He filled the tube with sand, and then he forced water into the tube, and he measured at the extreme of the tube the amount of the flow and the hydraulic head, which is quite easy to do, this experiment. Basically, what he did was